Добрый день, меня зовут Алиса Шевченко.
Hello, our name is Alisa Shevchenko.
Низкоуровневой безопасности.
I'm a researcher of low-level security researcher, and I'm also the first female winner in a security research competition where we researched various zero-day exploits. I am particularly interested in studying hypervisors to escape virtual machines, also remote execution of code in browsers, and also reverse engineering of various firmware, particularly digital modems. I am also the founder of Zero Day Engineering, which is a training company. We run trainings from the areas of my personal expertise.
Вся информация в этом докладе основана 100% на моей личной.
All information in my presentation comes 100% from my own research projects. I'm not affiliated with any company.
За исключением своего индивидуального тренингового проекта.
Well, except for my own training company, that is.
Доклад будет на английском языке.
I am going to make this presentation in English. However, you will be able to ask your questions in Russian afterwards.
My talk is split in 3 parts. I'm not sure that they will fit because we only have about 20 or 30 minutes. So first part, I want to give a big picture of attacks, modern attacks on browsers for remote code execution in order to place our topic into the context. In the second part, I narrow down to Google Chrome and its V8 JavaScript engine. I will explore several vulnerabilities that were found and zero-day exploits demonstrated in the recent few years. And lastly, in the third part, I prepared a deep dive into one specific vulnerability in Google Chrome that was exploited in a zero-day exploit in late 2022. This talk is about attacking browsers. Browser is probably the most popular system on computers and mobiles. Probably the highest user base that you can think of. And my talk is about executing arbitrary code in the browser. I want to stress that I'm not talking about vulnerabilities in web applications such as XSS, cross-site scripting, and cross-site request forgery. These vulnerabilities are located in the web application, but instead I'm focusing in this talk in vulnerabilities that resided inside the browser code. And I will, in this talk, focus mostly on the recent years because the state of the art of attacking browsers changes really fast. And I want to present you a very modern picture of what we have today. So in order to attack a browser, to execute arbitrary code on the system where a browser runs, typically this type of attack involves a one-click involvement with the user. So a user receives a link and has to click it. After that, arbitrary code would be executed inside the browser. In order to attack a browser, we must consider the attack surface. So in this slide, there is a very simple picture. Usually, for this kind of research and assignments, I prepare a visualization. You have to consider that attack surfaces are, there is a lot of attack surfaces in each system, and sometimes they are nested into each other, sometimes they overlap, and each one attack surface can consist of multiple attack vectors that can be used to inject the exploit. It is very important for us because if you want to find a vulnerability in the browser and make a zero-day exploit, you have to make a choice of what exactly you will be targeting. And your first choice will be whether you're targeting the browser source code itself or the JavaScript engine. So let's start with the browser attack surface. A browser's largest attack surface is the document object model. It is the backend which processes the HTML code. So after the HTML code has been parsed in the browser, which is done by the parser, the backend will prepare a system of classes that represent whatever you supplied in the HTML code in the browser. Next, in the browser, there is a large attack surface which consists of various file formats, such as graphics, video, audio, PDF, XML, and so on. In the browser, there are also networking protocols, such as HTTP2 and JSON. And of course, in the browser, there is the JavaScript engine, which is responsible for executing the JavaScript code. Also, there is a separate attack surface, which is a sandbox, but it is usually not reachable for remote attack. It's only used for elevation of privilege. So let's narrow down to JavaScript engine. It is the largest attack surface which is relevant today. You know, if you are not a specialist in this field, you probably think that JavaScript is something relatively easy. It is considered to be an interpreted language. So you assume that there is a parser, then there is an interpreter, and some internal built-in logic. But in reality, modern JavaScript is very, very complex. It consists of multiple stages and multiple subsystems which process the input JavaScript code. It's starting with a parser, analyzer, then interpreter kicks in, which processes the bytecode. A modern JavaScript engine would have multiple stages of compilation and multiple stages of optimization. In addition, there would be some interfaces which interact with the browser itself, such as interfaces to the document object model. So when you want to attack a browser, your first choice is whether you want to focus on the browser source code base or the JavaScript engine. And there is no easy answer which one is best. It depends really on many variables, such as your long-term goals, what you want to achieve, and what resources do you have, skills, tools, and so on. In any way, both of these two attack surfaces are very relevant, and they are the best if you want to attack a browser. In this talk, I will be mostly focusing on JavaScript engine, because it is much more complex, and it has a better potential for finding vulnerabilities in the long run. Also, attacking JavaScript engine is a multitude more complex and hard than attacking the general side of the browser. Because typically, all JavaScript engines are open source, and they are relatively well audited, so there are not so many vulnerabilities that you can find. The issues that can be found in JavaScript engines nowadays are very subtle, and it's really non-trivial to understand a typical JavaScript vulnerability if you haven't invested many months into researching this kind of vulnerabilities. There is a few things that we need to know about modern JavaScript engines in order to understand the security perspective. They are based on the ECMAScript specification, which is an open source specification. It changes very fast, which is the reason why JavaScript engines will have more features added. There is always some new technology that will be added into a JavaScript engine. Another thing that we need to know about a modern JavaScript engine is that it is really more like a very, very advanced compiler. It is not only an interpreter, but modern and mature JavaScript engines such as V8 or SpiderMonkey from Firefox, they will typically have multiple layers of compilation. So it starts with an interpreter, parser, interpreter. After that, there would be a few compilers involved and several stages of optimization. Each one of the stages represent a separate attackable source code. So on the right side of the slide, there is a photo from the very classical book on compilation theory, which is compilers by Aho and collaborators, which is the first book that you would like to read if you want to understand how modern JavaScript engines work and how vulnerabilities in them can be found. The next thing I want to mention is like a side notice about general offensive vulnerability research, is that typically a class of systems will be dominated by one or two classes of bugs. And I want to stress that this is not because some security researcher decided that we will start finding type confusion vulnerabilities in JavaScript, and so we have a lot of them. But this situation is dictated by the design and implementation requirements of systems. For example, hypervisors, my second favorite topic, are typically dominated by uninitialized variable vulnerabilities and race conditions. This is because a hypervisor typically involves a communication interface between the virtual machine and the hypervisor. So there is a lot of data flowing back and forth, which involves buffers. And if some of those buffers are not initialized, it's possible to leak some interesting information, for example, in the uninitialized buffer. Similarly, this kind of communication typically involves shared memory, and shared memory is very prone to race condition vulnerabilities. In browsers, in general, a very popular bug class is use-of-free. This also directly follows from how browsers are implemented, because they are based on high-level C++ classes which interact with each other in a very complex way. So there are many potential for producing some dangling pointers and use-of-free bugs. Finally, JavaScript engines are very famous for their type confusion bugs, for the reasons that I explain now. So there is a few trends in offensive vulnerability research of JavaScript engines. The first trend that you can see is that there is a lot of type confusion bugs. For example, there is a screen from the Google Chrome vulnerability history. You can see that literally every second, or maybe more than 50% of vulnerabilities in JavaScript engines are type confusion. A type confusion is a situation when some structure in memory is accessed in an incorrect way. So the code assumes that we're dealing with a structure of type X, while in reality there is the outline of the structure of type Y. Because of that, there would be some state corruption, memory corruption, and producing a potentially exploitable state. In JavaScript engines, this kind of bugs are dominating because of the properties of the language. We know that JavaScript is dynamically typed. There is no information that can be deduced statically about which type is a particular object or what is its shape. For example, we have an object and it can have different sets of properties. The different objects with different properties will have a different shape inside memory. And this information is only available at runtime. It means that the JavaScript engine has to determine what is the type that we're dealing with right now in runtime. And quite frequently, there can be a mistake here. This kind of bugs is not very popular in typical C++ code bases, because in C code, usually when we have a type conversion, so it is statically typed, we have static types, and if you want to convert something, you do something like static cast, for example, or some more advanced pattern. Anyway, in order to produce a type confusion in C++ code with static typing, it really involves a very major mistake by the programmer. But in JavaScript, it is much easier because typing is done at runtime. So there are a lot of subtleties that can produce this kind of vulnerability. Another trend for JavaScript engines, this is a very important one, is basically when we have some C++ code executing in the JavaScript engine. And then this code triggers a call back to the JavaScript runtime. And JavaScript code is executed in the middle of the C++ code. But C++ code is not aware of this situation. And it continues to carry on with its assumptions that were before this execution. But the JavaScript callback that was called, it could change the state of the memory very considerably. It could change all the structures and types completely. The result is that when execution continues in C++ code after the JavaScript callback, the state of memory is already corrupted. And the code will write something in the wrong place, corrupting memory, and this produces an exploitable pattern. For example, on the right side of the slide, there is a few samples. Actually, there are many, many ways how this kind of side effects can be produced in JavaScript. One example is that in JavaScript, we can redefine a prototype. A prototype is the fundamental object from which all other objects are inherited. And when we're looking for some attribute or function on the object, the engine will do a traversal to the prototype chain in order to find the handler for the particular attribute. So we can redefine the prototype, and we can provide a custom function that will be called in this moment. The result is that while the C++ code is iterating through the prototype chain, at the same moment, the JavaScript code gets executed and changes the memory state completely, and memory corruption. Another example, for example, assume that you have typed array such as uint32 integer array. You know that a typed array will contain only integers. And you have some object, and you assign the object to the type array member. This is where an implicit coercion happens. So the object must be coerced into an integer. For that, object must provide a special callback named value of, which also can be redefined. The result is that while C++ code is directly assigning integers, there is some JavaScript code executing that can change the type of the array, for example, and make it into something different. There are many similar patterns that can produce this kind of vulnerabilities. Another large trend for modern JavaScript engines is optimization issues. As I mentioned, modern JavaScript is very, very heavily optimized. There are multiple layers of optimizing compilation, with all the classical approaches to optimize, such as dead code elimination, optimizing for specific types, and so on. The JavaScript is forced to execute very fast. So what happens, for example, assume that you have some function that accepts an argument in JavaScript. You call this function, inside there is some access to the argument. You call this function multiple times and provide it with the object of type typed array, for example. The JavaScript engine will produce a specialized code which is optimized for typed arrays, meaning that it will have assembly instructions that access memory directly as we are dealing with a typed array. Now, what happens if you call the same function with a different type of object? Normally, the function should be de-optimized, meaning that the compiled code is discarded and the execution falls back to interpreting. Sometimes JavaScript engine would have a bug where a code does not get de-optimized in such a way. It means that the function will take your object, which has some particular shape, and it will access it in the same way as it was a typed array that we have seen before. Obviously, there is also memory corruption, and this kind of issues are almost always exploitable. I think to mention here is that optimization issues in modern JavaScript engines such as V8 are really very subtle. They are not as easy as I show in this example. So these are the three trends that you have to be aware of. When you start finding vulnerabilities in JavaScript engines, typically you would most likely stumble into all three of these trends. Now, I wanted to make this talk focused only on vulnerability research mostly, but I want to give you just a quick example of how this type of issues would be exploited. Here is an example of exploit that I wrote for Microsoft Chakra Core engine. Currently, it is not used anymore. It was replaced by V8. On the left side, there is a pattern in the JavaScript. You can see that there is a function. Inside the function, there is no information about which types are used here. Consider that we're calling this function with the first argument being a typed array. So the code would be optimized for accessing a typed array, meaning that it will access memory and read the integer values from the memory directly. And if we try to write something to the member of the array, it will be written as an integer. So after optimizing the code in such a way, we give it as an argument an array of different type, not a typed array, but a normal array, which can contain pointers to objects. So in this kind of array, there are not integers, but rather the pointers to objects are placed in the slots. So normally, when this situation happens, the code should be de-optimized. But in this bug, there was issue that the optimization didn't happen. So what happens in this case is that the function, the code that implements this function will take the address of our object that we provided and write it inside the array as an integer. It means that we can obtain the address of the arbitrary object in JavaScript and read it later from this array. Based on that, I built a primitive for getting the address of arbitrary object. The next stage would be to get the stack. Due to how objects are implemented in Chakra core, if you know the address of an object, you can, by a certain chain of logic, deduce the address of the stack. After that, finally, when I have the address of the stack, I can simply write my ROP shellcode on the stack and then trigger its execution. You can see that in my shellcode, this is the first stage. It only calls the virtual protect to make some executable memory region to drop the shellcode. In the full exploit that you can find on my GitHub, there is multiple stages which include also a continuation of execution. This is a very rough logic of how a typical exploit of a type confusion will proceed. In reality, it would be more complex, but I think that in some abstract way, this is basically the same logic that you would use to exploit a type confusion in JavaScript. Now, in the second part, I narrow down to Google Chrome and its V8 engine. In order to investigate the offensive attacking trends of Google Chrome, there are two large sources of information. The first one is observing the bug tracker, because Chromium is open source, and so is V8. So in the bug tracker, we can see all the bugs that were reported and patched. Typically, in the security advisory that is released, you will find some announcements of the vulnerabilities, but this is just this would typically be only a part of bugs that are actually found. So if you just dig the tracker, you will find a lot of vulnerabilities that were found, and you can analyze them to deduce some patterns. The second source of information is to take a look at the zero-day exploits that were shown for this browser. For example, Google Chromium was attacked with zero-day exploits about 10 times in 2022. On the right side of the slide, there is a screenshot from Hacker News. About 50% of zero-day bugs that were shown were in the V8 JavaScript, and others were in Google Chrome itself. Both of these sources of information are very interesting, but of course, the information about zero-day bugs is more important. But the problem is that this type of bugs are usually not disclosed for a very long time. So after they have been patched, you will see probably many months will pass, and Google will not disclose them at all. On the other hand, the bugs that are resided in the tracker, they will be disclosed after 6 weeks after the bug was patched. So this is part of the reason why part of my work is reverse engineering the patches. Because V8 is open source and Google Chromium is open source. So technically, when the patch is released, we can just look at the patch and deduce some information about the vulnerability, and maybe even write the exploit. I want to say that it is very, very non-trivial, as probably you will see later in the slide. But in general, it is quite realistic. And another interesting point to notice is that there is a patch gap. We know that Google Chrome is being patched very, very fast. Usually, the patch cycle is very short, and if there is a vulnerability, the patch is released, and users will get notified, and the browser will be updated. But V8 engine is also used in other softwares. For example, you know the Electron framework is based on Google's V8 engine. It means that all the vulnerabilities that affect V8, they also affect Electron. And you also know that Electron framework provides a foundation for building many, many very popular and important applications, such as Skype and similar things. In addition, V8 itself is also used in many different softwares. So the net result of that is that when there is a vulnerability in V8, it will affect a really broad range of different software, not only Google Chromium, but also Electron framework and everything that is based on it, and maybe some other software as well. And these other softwares typically are not patched as fast as Google Chrome. For example, Electron framework has a patch gap of about 2 weeks in the average from the moment when the patch is released by Google, and only after 2 weeks, Electron framework will cherry-pick the patch and deploy it to its users. Other softwares, such as, for example, Dota, has been recently reported with a V8 bug from 2019, I think. So there is the patch gap, which is 4 years. Let's take a look at recent Chromium bugs. I will be mostly looking at V8. Here is first example. This is a vulnerability in V8 that was exploited at Pound competition 2019 in order to attack Tesla infotainment system, which relies on Chromium and V8. On the left side, there is a patch. And in the patch, and on the right side, there is proof of concept. You can see in the patch, the red piece of code, it did some check that the regular expression is not modified. And after that check, there is a call to runtime. You see in the last line, object to string. It calls into the JavaScript runtime and basically calls some JavaScript code, which means that the JavaScript code that was called here, it can change the state of the system and modify the regex. On the right side, in the proof of concept, you can see how it works. There is some regular expression here, and there is an object with a function named toString. This is the one that will be called here, as you see in the patch. And inside this callback, the line which says red.x equals 42 is the one which corrupts the shape of the regular expression. Because when we assign a new attribute to the object in JavaScript, the shape of the object will be changed completely, and basically it's a different layout in memory, at least in V8. This is how it happened. It's a little bit more complex here because the proof of concept involved two callbacks to JavaScript. One is toString and another one is value of. But the basic idea here is that after the regular expression has been already confirmed that it is not modified, intact, it calls back into the JavaScript, and the JavaScript code corrupts the shape of the regex. And meanwhile, the code here, after the patch, it continues to carry on with its past assumptions about what is the shape of the regex. This is the basic idea. The exploit itself is more complex. You can find it in the tracker if you're interested. So this is an example of a very typical vulnerability in JavaScript engine, which is related to JavaScript callbacks. Another example is vulnerability from 2021. Similar idea, same bug pattern, that we have some JavaScript which implicitly calls into the JavaScript runtime again, while executing some code in C++. In this case, this is related to a handler which is assigned to the HTML element named embed. The embed element has a property named onload, which can be assigned with a function that will be called when the embed is loaded. So when the basic idea here is exactly the same, that C++ code makes certain assumptions, then the handler gets executed, JavaScript code corrupts the state, and memory corruption follows. The patch here is a bit non-trivial, so I will not attempt to explain it, just for the reference. And there were several bugs of very similar type, also related to handling of document object model elements, HTML elements. The vulnerabilities in V8 optimization are very, very subtle nowadays. There are no blunt patterns, like I explained previously in the slide. There are only very subtle patterns that require a great amount of understanding how optimization works in order to even begin to understand them. So I just dropped some links here. There is still a lot of vulnerabilities in optimization, but they are definitely very, very complex. And this kind of vulnerabilities typically cannot be found by static analysis, or at least it is very non-trivial. Usually it's fuzzing. Another interesting pattern. This one is really interesting because it is a special bug class which affects only Google's V8 engine. At least it hasn't been shown anywhere else. So in V8, it has special types of values that are used as sentinels in order to mark special conditions for the code. For example, in order to mark some properties that have been deleted or to mark uninitialized values in the array. This type of values are called oddballs. And it has been shown just a couple of years ago that when such a special sentinel has been leaked to JavaScript code, and you as a JavaScript coder, you have in possession this kind of special sentinel, you can then use this sentinel to produce memory corruption and code execution. This is quite remarkable. So, for example, here is a snippet of the code. There is a special value named the whole. It's basically just some integer value which has a special meaning inside the engine. And this value is used in several places in the code in order to indicate special circumstances. For example, it is used to indicate uninitialized arrays or other structures. And it is also, like in this code, it is used to indicate some special elements of a hash table that have already been deleted. Which means that if you have the whole value inside JavaScript, you can craft a special type of hash table. For example, it was demonstrated with object of type map. So you craft a special map, and you assign the whole value to some members of it. And internally, JavaScript engine, when it will be parsing the map, it will find the whole value. It will treat it in a special way, like a sentinel. And it will think that a particular value has been deleted, but in reality it was not, because you just dropped the value there. And memory corruption follows. This is a very interesting pattern, and there were several bugs with this pattern. One in JSON stringify code, which leaked the whole value through some exception, and another one in promise any call. There is a different pattern that when a promise array capacity was calculated here, some extra capacity will be assigned with holes in order to indicate uninitialized state. And there was a miscalculation of the size, so that having an array of promises, you was able to access this uninitialized value and fetch the whole value from there. You can see, for example, there is a proof of concept, and it shouldn't make sense to you unless you are very familiar with JavaScript vulnerabilities. This is a very common situation. Similarly, in any proof of concept code that you can see, even this our first example, which is basically the simplest vulnerability that I can think of, it shouldn't really make sense to you. Because as a JavaScript developer, what is going on here is some nonsense. But when there is a vulnerability, it triggers state corruption in a very precise way and allows us to execute arbitrary code. That was my review of several bugs in Chromium. And so to summarize, the probably most popular bug class in V8 is still various optimization issues, but they are really very subtle and really complex. And another important trend is the emergence of special bug classes such as the whole, which affects the engine systematically, and it doesn't really affect other engines. The bugs of the type like this one we showed for Tesla is really, they're really very rare nowadays in V8. Actually, I was surprised that the vulnerability was found in 2019, but usually I'm not seeing this kind of vulnerabilities in V8 anymore. Now let's move on to our case study. I will very quickly just give you an idea. So I was looking at the vulnerability from 2022 that was exploited in a zero-day attack against Google Chrome in late November and December, I think. It was patched already. The bug is still not public. I mean, the information about the vulnerability, it has not been disclosed, so now it is May. It means that at least 6 months, Google is keeping the information about the vulnerability and not disclosing it. So I decided to look at the patch in order to reverse engineer it and maybe try to write the exploit. Here is, so the patch actually is quite large. I cannot show it on one slide. On this slide, I'm showing you just some very relevant points. So in the announcement of the patch, you can see that it is a bug in the parser, and it is related to fix eval tracking. Due to mismatch in strictness, we otherwise invalidly mark scopes as calling sloppy eval. I want to say that just looking at the description of the patch and looking at the patch itself, it doesn't make sense at all how this can be exploitable or what is even the security impact here. It's absolutely not obvious. After reverse engineering the patch, which took some time, I was able to reach the code that was patched, and but still it was very far from obvious how it can be possibly exploited. Turns out that the triggering of the bug is quite complex. On the left side, you can see the proof of concept here. It requires some special arguments passed to the runtime. If you're familiar with JavaScript, you can see that the first function is basically emulation of a garbage collection. You know that in JavaScript engines are garbage collected, and in order to, typically when we have some dangling pointers or some pending changes in the engine, we have to trigger a garbage collection in order to purge some dangling pointers or whatever was used. So garbage collection is usually involved in triggering vulnerabilities. And the first part of the proof of concept here shows an emulation of the garbage collection. And the second part of the proof of concept is the actual, what triggers this bug. On the right side, you can see the impact. There is type confusion of very, very uncommon class. The information here says that there was some expectations of a property cell, but found a feedback cell. I want to say that this is not a common pattern of type confusion, and I haven't seen a history of vulnerabilities with this kind of type confusion. So it really didn't make sense to me until I analyzed what is going on here. So in the proof of concept, you can see that there is some quite complex assignment. There is a loop. Then there is a class. A class is announced. Inside a class, there is a call to eval. There is some other things going on. Then there is the arrow function involved. And that's it. So in order to understand what's going on here, by looking at the patch, it's absolutely not trivial. So first thing we need to know is what exactly is sloppy code that was announced in the patch. The patch says that there is some mismatch in strictness. So in JavaScript, there are two modes of execution: sloppy, which is the normal mode, and strict mode. Strict mode is a special mode which provides some additional guarantees for security of high-level applications. The thing that we need to know about the strict mode is that it is invoked automatically when we have a class. So whenever you're announcing a class, its internal code will be executed in strict mode. Also, if you have a model in JavaScript, JavaScript modules are also executed only in strict mode. The next thing that we need to know is eval function, which executes JavaScript code, has an interesting property that it can access variables in the surrounding scope. So here's a snippet of code. Here you can see we're calling eval with some announcement of a new variable, var a, and we can see that this variable can be accessed from the outer side scope. Similarly, the code inside eval can access variables in the surrounding scope. Now, this is very important from the position of parsing, because whenever the JavaScript parser sees evil, it has to factor in the possibility that evil will be accessing surrounding variables or even introducing them. It means that it has to make a correction for providing extra storage for variables that evil can introduce. Another piece of theory is the arrow function, which you should be familiar with. It's just basically a simplified pattern of announcing a function in JavaScript. You just have a round parenthesis, then there is an arrow and expression in the simplest way. Now, the problem with arrow function is that it is not possible for the JavaScript parser to see that we're announcing a function here until it has parsed the expression completely. So with these pieces of theory, we can look at the proof of concept again and see what's going on here. So there is a class which has been announced. We know that classes should be in strict mode. And inside there is an eval call. So in this situation, eval should not be introducing variables into the surrounding scope because it's already been in strict mode. And in order to track eval calls, the parser, well, it does some special tracking of eval calls whenever it sees them. And when it sees an eval call, the parser has to notify the surrounding scopes that we have seen eval and change some properties of the variable storage. Now you can take a look at the patch. It should start making a little bit more sense. In the original code, on the left side, we were basically just recording the eval call inside the proof of concept. On the right side, the patch added a check, which checks whether we're in the sloppy mode or not. It means that in this proof of concept, because we're not in sloppy mode inside the class, it's in strict mode, so we should not be tracking eval here. It doesn't need to be done. This is basically the idea of vulnerability. The patch itself is a little bit more complex. I just explained the core idea. So the result of this is when this code executed, the parser would treat eval as it is sloppy, and it will notify the surrounding scopes. It will allocate some extra variable space, and so on. Well, in this situation, it is not necessary. So why is it a problem? Consider on this screenshot, this is some dump of feedback slot. I'm skipping a lot of things here just to fit in the time. You can see that we have a pattern of type confusion with a feedback cell. So on the next slide, what I did, I dumped the feedback cell, its contents, and you can see that slots contain the names of the JavaScript opcodes that will be executed. On the left side, it is the normal situation that should be observed in our proof of concept. On the right side, if you look closely, you can see that slots number 1, 7, and 13 contain an extra opcode, which is named load global, not inside type of. It's basically an extra JavaScript opcode which forces the engine to look up the variable in the global scope or in the surrounding scope, as opposed to looking it in the current scope. So normally, if without the vulnerability, we should have the picture which is on the left. There are 3 calls and defined named own opcodes. But because there was the vulnerability, eval was marked as being sloppy. So JavaScript engine injected additional opcodes, load global, which instruct the engine to look up the variables for eval in the surrounding scope. And the type confusion happens when on this slide is. So this is the dump of our feedback cell that was type confused. You can see here that this one slot number 7. This is the culprit, and you can see there is the type of feedback, which is feedback cell. Feedback cell cannot be the type of feedback for this opcode. it can only be useful for a JavaScript call. So there is some confused feedback here because this opcode was injected because of the sloppy eval marking. But the feedback for it is incorrect. On the right side of the slide, there is the enlarged picture shows the spot where type confusion happens. So you can see here the typecast failed. This is exactly the reason why it failed, because we expected to find a property cell for the type of opcode load global, but instead we found a feedback cell. There is a bit more complexity involved here, just giving you the general idea. So from here, you can already see how it can be potentially exploited. We would need to craft malicious feedback cell, craft some malicious feedback, and probably we can coerce this state to some well-known type confusion pattern that can be further exploited. So exploit is out of scope here. This vulnerability is very interesting because it is in the parser, and typically nowadays I'm not seeing vulnerabilities in the parser at all. And also because the type confusion pattern which is involved here is really non-trivial. This is not the kind of bug that can be exploited very easily with some well-known prepared primitives. So this was already exploited, so we know for sure that it is exploitable and the exploit can be written, but my estimation is that it won't be trivial. References for you is some links on the bug tracker and V8 website with the building instructions. The patch to the vulnerability that I just discussed, you can also find it. Here is the link. For vulnerability analysis, really, the #1 source is digging Chromium bug tracker and V8 bug tracker. Another interesting link here is V8 patches review, which is patches specific to V8 engine. This is the end of my talk. Now there is, I hope we have some time for the questions. Есть время для вопросов? 5 minutes. 5 минут для вопросов, можно по-русски.
So we have 5 minutes for a Q&A, and you're free to ask your questions in Russian if you so choose. Of my questions, it's a shame they cannot be heard online. I'm afraid, had I even been in the room, I wouldn't have been able to hear them. Oh, good, he's getting mic.
Спасибо за доклад.
Hello, and thank you very much for this presentation. My question is more general. Why are we still using JavaScript, if it's riddled with issues?
Хороший вопрос. Но на самом деле
Ain't it a good question?
борются. И в частности, та уязвимость.
Well, people are trying to change that, aren't they?
Evil.
So the eval vulnerability pattern I've mentioned is so well known, and it triggers so many vulnerabilities in web applications as well.
5 или 6
Well, it has created so many issues that, AtmoScript
сделали так, что если evil
in version 5 or version 6 made it mandatory that, if evil is run in strict mode, it won't create those issues with accessing the external scope. So the general trend is that people are trying to address that, but I don't think you can run away from JavaScript
стараются как-то улучшать.
because it brings in so much dynamism to browsers. That's why people try to improve it. Thank you very much. So, the vulnerability you described in part 3 of your presentation enables us to pull entities from external scope. Did I get your idea right? No, well, it's a bit more complex. I've just dropped some important details here. The scopes are all invoked when we get very close to type confusion.
Проблема в том, что
The problem,
изначально связано это с фидбэком, который генерирует.
and it's due to the feedback being generated. So initially, normal code is generated. So these feedback cells, they're in normal order and they contain normal feedback. But then at a certain point in time, a particular situation arises where a JavaScript engine introduces opcode so that eval can take a look at global code, and then they are added to the wrong slots. And because they are there, this leads to type confusion because feedback there is very different. In other words, we are getting a feedback cell that should have happened later. Sort of. I mean, it's all very complicated. On V8, feedback cell consists of several classes that talk to each other. So feedback is separate from metadata, and that's the crux of the problem. That I understand. But you've been talking about calls here and type check, right? So I don't really see how it's exploitable. We'll need to be able to exploit it. No. So with typeset, in debug build, we will have this issue, but in the release build, so this is a debug check. All right. So you're effectively telling us that the release build will not trigger it. Absolutely. The release build will have state corruption and memory corruption. Gotcha. Thank you very much. Is that it? This will be the last question. So you mentioned that you reverse engineered patches. Do you do that manually? Or to use any automation in order to make sure you're not looking at something that's got nothing to do with a particular vulnerability. I'm trying to be flexible depending on the nature of the patch. So first thing I do, take a look at the patch to see what roughly it does. And then I will either do sort of emulated fuzzing, like if I have any hypothesis about triggering a particular vulnerability, I can, do quick and dirty JavaScript code and fuzz it. Alternatively, if I don't really see what kind of JavaScript code could be there, I will be analyzing the initial JavaScript code and the patch itself. I will need to read into the semantics of the patch and see what kind of data is coming in. In that case, was static analysis through and through because I had no other ideas. So that was fully manual analysis. Absolutely. For sure. Most patches are analyzed manually. With JavaScript, some things can be fuzzed, and that can be helpful at times, but patch analysis in most cases is manual. And I can guarantee that for V8, it is 100% manual because it's so damn complex. Thank you.
Спасибо за внимание.
Thank you very much.